Welcome to the Conscious Artificial Intelligence project. Glad you are here. Today we are looking in deep some code optimizations found in the uvolume unit in regards to AVX and AVX2 assembler code. The host application was created in Object Pascal, but whatever we are looking here does not depend on the host application. We are looking in deep on the actual AVX, AVX2 assembler code. So let's start. Here we have the same testing application from the previous video. I'll quickly run. So what we are doing in this testing application, we have two vectors with 1000 elements each. They are of the type of single precision, and we are running 20 million times the dot product. So let's see what happens. Run. I will run to 2.7 seconds. That is about what we got before. And in the previous video we didn't calculate the actual speed. We calculated 20 million times dot product with 100 elements. Using 100 elements per vector, we were getting 9 gigaflops. Now we'll do the same calculation, but to check how much we are gaining by using bigger vectors, how much we gain in gigaflops. The actual code for this dot product is here. I'll make this screen bigger. We'll go in deep how this code works later. At this moment I will just calculate how many gigaflops we are getting. This computer is a slow computer. It's an i7 with burst speed of just 2.4 gigahertz. So considering that we are using a processor that has only 2.4 gigahertz and we are already here getting 9 gigaflops per core, you can see we are getting a very good result. So calculator. We have for each element in the array, we have a multiplication, then we have to get the result of this multiplication and add to the total. Therefore we have two floating point operations per element in the array. So for us to calculate the actual speed, I'll calculate here 20 million times the vector size times 2, because I have two operations per vector element, and then I would divide by the actual time, 2.7 seconds. And let's see how big is this number. We have here 14.8 gigaflops. So that's, you can see how much gain we get in running a bigger array. Okay, so let's have a look at the actual assembler code. In the case the input array is too small, I have a risk of wasting computing time in going through this algorithm. So the first test that is done here is a shift logical write. In this code there is inspiration from maybe a more than 10 years old source code that I actually helped to debug, called Essentia. And if you look at this code and that older code, you'll find some similarity. Anyway, we have a shift logical after here that is actually the same thing as divided by 32. So Cx has the number in this code is the number of elements in the array. This is Cx. And then I have a pointer to the first array and a pointer to the second array. Okay, so after doing this, I have divided by 32. In the case is 0, I'll skip this large block. What is the large block? Is this block here. Okay. This operation here, the goal is just to zero, register 0, and then I do the same thing for register 1 here. So here we go through the large loop. What I will do is I load the elements from memory, then I multiply these elements by the other vector. This is what is done here. And these elements are then summed to register 0 and 1. Why? This is the first thing that you might notice. Why I'm not just summing everything to 0? This is made to be able to run these two commands in parallel. I am making theoretically possible for the processor to run in parallel. We could go, actually the previous version of this code actually had here, instead of 0101, it was 0123. The problem is, in my particular usage, I deal with small vectors. And on Windows, on Linux there is no problem. On Windows, YAM6, YAM7 are not. You need to push these values into the stack to be able to use safely, because the calling function might be using these registers. So that could be a further optimization, but in my specific case it doesn't make sense, and I came to this conclusion after some testing. But anyway, so we have two registers being used by for summation. We have YM0 and YMM1. You can see that there is no dependency on these two. Then these two can also be used in parallel, and these two can be used also in parallel. Here is even better. On the beginning of the loop, all four commands can theoretically be run in parallel. And that's an important thing, in my opinion, when writing optimum code. Even if the processor you are using is not able to run the next four operations in parallel, allowing your code to be theoretically run in parallel, it kind of gives you certainty that future implementations of processors might end using a better code. In the case AVX2 is not enabled, you have just AVX. Then there is this other implementation here that does exactly the same. Here I have only 4 commands. Here I have 8. And you can see these 4 commands here also do not have any dependency on each other. They can be run again in parallel. So that's very efficient. And maybe this is one of the reasons why in my own computer I see no difference between running AVX2 code or running the other AVX code. It is exactly the same. So now maybe it is becoming clear to you why I am dividing the number of elements by 32, because I am running this code in chunks of 32 elements. There are some reasons for doing this. One, here I am advancing pointers on these arrays, and here there is a loop. So the larger I make each chunk, the less overhead I will have with advancing pointers and looping. So that's one reason. The other reason is, if I have 32 elements, I can do things like this, that is creating a number of commands that can be run in parallel. So that's good. Well, then you could say, well, why don't I make 64 or even 128? That's a valid argument. The problem is, if you have an application that has a big number of small arrays, then that becomes a problem. And unfortunately, this is my case. It is frequent that I have arrays of only 27 elements. The motivation goes beyond this presentation. I eventually make a video about this in image processing, that I need just 27 elements, but I have to do dot products literally billions of times of small arrays of 27 elements. So in the case I do not have a minimum of 32 elements, I go to the small loop. The small loop, instead of using YAM, these registers here, I presume most of you watching this video know they have 8 single precision values. So and 8 times 4 is 32. That's why we have here 32. Okay, and then if I have less than 32, I'll divide by 4 the counter. The counter is protected, the number of elements is pushed and popped, so it's safe. I can come here and divide by 2, and here there is something very, very important. I was having a number of problems that I couldn't explain. Sometimes the speed was high, sometimes the speed was low, and they couldn't explain the problem. When you stop operating with registers that contain 8 elements and you start working with registers that contain only 4 elements, these additional registers that are not in use anymore might provoke stalls on your computation. So the way to prevent this, when you stop using YAM and you start using XMM, then you have to call zero upper. Otherwise you start getting stalls. And then this code, these two lines can be run in parallel. These two cannot. Why? Because I'm storing the result of the multiplication here and then adding here. Given that this portion of the code will not be run many times, is not a big problem. So what is important in this code, what is really important, is this portion of this code to be efficient. There is something here that I haven't told you. At the end of the large loop, I have two 8 elements vector long with the result of the summation of the dot product, that is register 0 and register 1. So I have to put everything on register 0, and then once I have everything on register 0, I get the high end, the chunk of elements that are not visible in XMM0. So it is the higher part of YAM. I will store this via V extract. I will extract this higher portion into XMM2, and then it's easy. Then I can have the result of the summation in XMM0. And then in the end, I do a little trick here. This is just done to have the summation of all elements inside XMM0, all 4 elements. The result of that summation will be stored in the first element of XMM0. And then and then you can do whatever you want from the result. So the main part here on that code, what is really important to remember, is the more you write commands that do not depend on each other is better. And the more you can do operations with registers only, without using memory, it is better. I could do a dot product. First I multiply everything, store in memory a partial result, then I do the summation back from memory and calculate the total of the dot product. I haven't tried this, but I presume it would be probably 3 or 4 times, probably 25%. Actually, you get the amount of time you take to run this, multiply by 4, that will be your result. That's a guesstimation. I haven't tried this, but from experience, this is what I would expect. Actually, thinking on this, I'll show you something. On the previous video, I talked a little bit about a function that multiplies and then adds. I'll show you the plain Pascal code. It's easy to understand. If you code in any computing language, you will understand this. Here we go. It is very common in linear algebra. First you multiply 2 elements and then you add. That's very common. Why a vector operation that does 2 things? Well, because it's faster, because if I do 2 operations and then I store in memory, it's more efficient. Okay, this is plain Pascal code. I will show you the equivalent in AVX assembler code. Here we go. The implementation is very similar to the implementation used in the dot product. Motivations for this development are similar. The number of elements in the array is stored in ECX. Here I have the pointer to the array, and then here I have the address of the value. I am using YAMM5 as the register that has the number that I'm multiplying with. v broadcast, you get this value and put this very same value stored in that memory position into all elements of this vector. Okay, so let's see the implementation. Here I have an ideal scenario that all 4 commands could theoretically be run in parallel. Then I have the very same thing here. I have an ideal situation again. All 4 elements are running parallel. And then again here an ideal situation. All 4 elements running parallel. This in part why, well, writing operations that can be run in parallel in part explain why if I get here 9 gigaflops per core, it means I am running more than 8 elements per clock. And given that I am processing 8 elements with only one AVX instruction, that means I am processing here more than one instruction per clock. So in part, the reason why this is possible is because I have instructions that can be run in parallel. It was coded in that way. And here I have way above. I have almost 2 instructions per clock, which is a lot. If you consider that in this code there are other things that are not actual calculation, like I have load from memory that is just overhead, and then I have store to the memory, just overhead again, doesn't count towards gigaflops. Then I have to update pointers, a loop, a jump. So I have a lot of overhead here, and even with all this overhead I can make more than 1 instruction per second. That's a lot. That's a really good speed to be at above 1 instruction per clock of useful work. That's really good. Okay. So the instruction is multiply and add. Here we have the load from memory. This instruction here does both things, does the multiplication and adds the value. Or if that's not enabled, the code is very clear. Here I have the multiplication and here I add. And that's the end, and I start back to the memory. Okay. I hope you have enjoyed the video. In the case you want me to explore something, or you have any question or any doubt, you can either comment on YouTube, or you can have a look in the project at SourceForge. You can post there. And I hope I will see you soon on the next video. Thank you again. Bye bye.